Okay, so for section 6.4, we are going to talk about the area under a curve, or the area between a curve and the x-axis. So we talked about in section 6.3 that when the graph is above the x-axis, then the definite integral is the area. So it represents the area between the graph or the curve and the x-axis. So if we look at this first example here, we want to find the area between the graph of x squared minus 1 on the interval 1 to 2. So we are looking at this piece, and we want to find this area. So the way that we are going to do this is the definite integral. So we're going to do the integral from 1 to 2 of x squared minus 1 dx. And when you do this, this is section 6.3, increase and divide for x squared and negative 1, and then plug in 2, subtract when you plug in 1. When you do all of that, you should get 4/3. Okay, but what if the graph is completely below the x-axis? So say it's this piece, right, from 0 to 1, the same function from 0 to 1. So let's do the definite integral and see what happens. If we evaluate from 0 to 1, this integral, we're looking at x cubed over 3 minus x, and this is evaluated from 0 to 1. We plug in 1, we get 1/3 minus 1 minus 0. So this is negative 2/3. So that tells us that the area, well, the definite integral is the negative of that area between the curve and the x-axis. So that actual area is 2/3. So what we would want to do here, looking at like that whole interval, right? So if we want to if we did this whole thing from 0 to 2, and so we would have this piece and this piece. We do the integral from 0 to 2 of x squared minus 1 dx. We would get, x cubed over 3 again, minus x evaluated from 0 to 2. Plug in 2, you get 8/3 minus 2. Plug in 0, and you get 0. So 8/3 minus 2 is 2/3. So if we look back at what we did before, we got 4/3 for the area, the positive area, and negative 2/3 for the stuff underneath, which is 4/3 plus negative 2/3 is 2/3. This is the area above, and this is the area below, and this is the definite integral there. So the definite integral represents the net area bounded by the curve and the x-axis. So it's actually, like, you can think about it, it's taking away some of this area. So it's that the bigger stuff minus the smaller stuff there. That's why it's getting smaller, because it's adding that negative area. So if we want to be really careful with that, and we instead want the total area bounded by the graph, but we don't want to think about the area underneath as negative area, what we're going to do is to get the total area, we're going to do the area above minus the area below. So when we do that, what happens, we would have 4/3 minus a negative 2/3, which would be 6/3, which is 2. And that would be the total area. Or you could do the area above plus the absolute value of the area below, and that would do the same thing. So to find the total area, what we're going to do is find any x-intercepts on our interval. And then we're going to split the integral up. So break the integral up at those values. And then you're going to take the absolute value of each piece. Or each area, right? And then add it together. So let's look at this with some examples. Oh, blast. I should have put these graphs on here for us, but I'll just sketch them. So from -1 to 1 here, this and this graph does this number. So this is -1. And this is 1. So to find this area, we'll notice that it's all above the x-axis. So we don't need to break this up. There are no x-intercepts. So we're going to do the integral from -1 to 1 of x cubed plus 2 dx. Straightforward, no x-intercepts. So this is just like section 6.3. You're going to evaluate that integral. You should get 4. If you do not, let me know. Or if you need help, let me know. But again, that's in section 6.3, and I don't want to take even more time doing those. So if you need help with that, though, let me know. If we look at this next example, and you can graph these in Desmos to look at them. This one is, we're looking at the graph of 3 over 2x minus 1 on the interval from 0 to 2. So this is 2. This looks like it's about here. And then this looks like this. So we would be looking at this area, which again is all above the x-axis. No x-intercepts on our interval. All above the x-axis, so nothing special needs to happen here. Just do the integral. So the integral from 0 to 2 of 3 over 2x minus 2x plus 1 dx. This one needs a u substitution, so I'll walk through that. So u is 2x plus 1 du would be 2 dx. So 1/2 du is equal to dx. So I have the integral from x equals 0 to 2 of, I'm going to put that 3 out here, 1 over u times 1/2 du. So then we have 3/2 times the integral from x equals 0 to 2 of 1 over u du. That's the ln of the absolute value of u from x equals 0 to 2 times 3/2. And if you just keep going, this got to plug that u back in to be 2x plus 1, and then evaluate that from 0 to 2. You should do some stuff. And then I got 3/2 times the ln of 5. And you can get a decimal approximation for that. That's fine. But I should see, most of that work on your paper. All right. For the next one, so again, none of these have been that different than what we did in the last section because none of them have had any area below the x-axis yet. On this one, we're looking at the integral from the interval from 0 to 4 of this. Oh man. So it looks like this, and it would just be this area, which is also all positive. Oh man. All above, no x-intercepts. So just evaluate this into this integral normally. So we'll be looking at the integral from 0 to 4 of 1 plus e to the negative 0.3 x dx. You need a u substitution here on this one as well. actually split this into two and to do substitution on the second part. So I did the integral from 0 to 4 of 1 dx plus the integral from 0 to 4 of e to the negative 0.3x dx. Do use substitution here. And then this is just x, and then evaluate all of that from 0 to 4. So u is 0.3x, du is 0.3 du, x, sorry. So then you would do 0.3 times 0 to 4 e to the u du. This is x equals 0, and then continue on with that. Again, just like we did in section 6.3. This eventually, once you continue doing this too, eventually you should get 6.33. The difference here is in this setup, not really anything else. Okay, so here's our first example where we actually are going to have an x-intercept. So let's graph this thing. So if we look at y equals x squared plus 3x plus 4. That's not right, minus 4. Oh, that's not what I meant, minus 4. Okay, and we are looking at the interval from 0 to 4. All right, let's do this. And let's take a picture. All right, so we have this graph here, and we want to know about the area from 0 to 4. Well, you'll notice that there's some below and some above, and that cross happens right there. That x-intercept we need to find. So our first step is going to be to find that x-intercept, which we're going to do by setting this quadratic equal to 0 and factoring. I need a 3, so plus 4 minus 1. First is x squared, outer 4x minus 1x, good, outer inner gives me 3x, and then last gives me negative 4. Okay, this x equals 1 or negative 4, but I don't care about the negative 4, I care about that 1. So I'm actually going to split this integral up at 1. So I'm going to go from 0 to 1 of this thing, and then add that to, I'm actually going to take the absolute value of this piece, and then add that to the area above. So that would be from 1 to 4. I don't need to take the absolute value of that because it's already positive. So once you do this integral, you'll get 13 over 6, or negative 13 over 6, and you're going to take the absolute value of that, and then plus this guy. Once you do that is, I have 63 halves. So then you're going to add those together. So this is the area. This is the absolute value of the area below. Plus the area above. And you get 101 over 3. So that would be the total area of this function trapped between this curve and the x-axis from 0 to 4. Okay, so splitting this up at that x-intercept, recognizing that the first piece is negative, so we want to make it positive, so take the absolute value, and then that second piece, it is already positive, so just leave it alone. Okay, so then some applications for this stuff. Marginal profit. of a certain style of sports jacket is given by P prime is 56 minus 0.8x dollars per jacket, where X is the number of jackets produced and sold weekly. Find the profit for the first 50 jackets that are produced and sold. Okay, so we need to find profit from marginal profit. We're going to take an integral. So profit is going to equal the integral of the marginal profit. And we want to know about the first 50. So there, that gives us limits on our integration there. So we would have the integral from 0 to 50 of 56 minus 0.8x dx. So increase and divide 0.8x squared over 2. And then evaluate that from 0 to 50. When we do this, you get, this is 56 x minus 0.4x squared evaluated from 0 to 50. So 56 times 50 minus 0.4 times 50 squared. And then minus, this would all be 0. I have 1800 once I put that in a calculator. So it's not really about area there, but it is about profit, making that indefinite integral a definite one, right? You're doing the profit for the first 50 jackets. So from 0 to 50. All right, so number 2, the marginal cost of a product is given by this thing. Marginal cost is C prime of X is 15 plus 4 times X to the negative 1/2. X is the number of units produced. The current level of production is 100 units weekly. If the level of production is increased to 169, find the increase in total costs. So we're going from 100 to 169. That's going to give us our limits of integration there. So we're going to do the integral from 100, increasing from 100 to 169. We want to find cost then, the increase in total cost. So we're going to take the integral of C prime. So 15 plus 4 times x to the negative 1/2. This is 15x plus increase to 1/2. Divide by 1/2 or multiply by 2. And then we're evaluating that from 100 to 169. So 15 times 169 plus 8 times the square root of 169 minus 15 times 100 plus 8 times the square root of 100. This is a lot of stuff happening. I have 1059 to end with. So the increase in cost would be $1,059. So again, the new thing here in this unit is that, or this section is that you have limits on the integration that you're doing. So you're not just finding the cost, you're finding the cost if we increase from 100 units to 169 units. Okay, so marginal revenue from a sale of bottles, X bottles of shampoo is given by this function. So R prime is equal to 8.4 minus 0.3 X to the 1/2. Find the increase in total revenue. So we're finding R. If the bottles sold is increased from 225 to 350. So what we're going to do is the integral from 225 to 350 of R prime. That would give us R from that, the increase in R. So we have the integral from 225 to 350 of 8.4 minus 3.3 x to the 1/2 dx. That's 8.4x minus 0.3 times x to the 3/2 times 2/3. Evaluate it from 225 to 350. So that's 8.4x minus 0.2 x to the 3/2. Evaluate it from 225 to 350. So do the 350 part minus the 225 part. I have 415.42. no, yeah, 415.42. So that is the increase in revenue if they make 125 more bottles. All right, and then this last page is more practice problems. Is this the last page? Yes, it's more practice problems. I'm just going to show you pictures of these. The first three are not, there are no x-intercepts, so you don't need to worry about breaking these things up, but the area, because the area will just be positive. 7 minus 2x looks like this, from -1 to 3. So there's nothing to do there. Let's make sure of that. 7 minus 2x. Yeah, so that happens past 3. From -1 is all above. All right, so this is all above. So you don't need to do anything special here. Just do the integral from -1 to 3 of 7 minus 2x dx. And that integral is pretty easy as well. Number 2, you actually do need to do a u substitution on this integral, but this graph, 3 times e to the 0.6x. We're looking from 0 to 5. So 0, 5, that's all going to be above the x-axis. All above. So nothing fancy needs to happen here. No breaking this up. Just evaluate from 0 to 5, 3 e to the 0.6x dx. Use a u substitution for make u 0.6x, and then go on from there. Then number 3, we are looking at x squared plus 2x minus 3. X squared plus 2x minus 3 on the interval from 1 to 3. That's 1. So 1 to 3 would actually all be above the x-axis again, so we don't need to worry about it. Worry about breaking that up. So just take the integral from 1 to 3 of that function, which is a straightforward integral. Increase and divide several times. All right, number 4, though, I think we're going to have to do some breaking up here. So x squared minus 2x minus 8. And we're looking at this interval is 2 to 5. So you can see that this at 4 actually crosses the x-axis. So let's go through, let's actually take a picture of that so we can make it look right. Okay, so we're looking from 2 to 5. And so this breaks up here at x equals 4. So that's what you're going to do. If you wanted to figure that out without a graph, you would factor this. Let's see. 8, 4 and 2, x minus 4, x plus 2, -8, -2. Okay, yep. So that would be x equals -2 and +4. We don't care about the -2. We care about that 4. So what you're going to do is the integral from 2 to 4. This would be the stuff below the x-axis. So you're going to take the absolute value of this stuff and then add that to the integral from 4 to 5, which is above. And so we don't really care. If you weren't looking at a graph, you would just take the absolute value of each of the pieces, find the x-intercepts, take the absolute value of the pieces. Because, if it's already positive, then it is going to stay positive, and so that would actually work fine. When you work this out, this part gives you negative 28 thirds, so you're going to take the opposite value of that and then add it to 10 thirds. So 38 thirds for your answer for this area. So work those out and let me know if you guys need any help with that. I would be happy to help you more. Just let me know. Thank you.